unit by tying up our last bit of information on buffers and titrations and going over the final little piece of new information on solubility. So we'll start with a couple buffer calculations to review the previous lesson. So let's do an example or two. In this example, we're making a buffer by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. The pH of this buffer we measure to be 4.74. We want to calculate the pH of this solution after 0.02 moles of sodium hydroxide is added. So recall, we've got a buffer solution, so we're expecting that it prevents the pH from changing too much. And just to review from yesterday, how this buffer is working is since we have dissolved sodium acetate, the sodium makes this a strong electrolyte, so we would expect that we have 0.3 moles of sodium and 0.3 moles of the acetate ion in our solution, which, since the acetate ion is the conjugate base of acetic acid, that means that not much of the acetic acid is going to initially dissociate because we already have a common ion. And so when we get to equilibrium, just as the buffer before anything else is added, we've got the acetate ion and acetic acid. We've got an equilibrium mixture of 0.3 moles of acetic acid and an equal amount, 0.3 moles of the acetate ion. So let's look at what we know so far. Before the reaction, like I said, the moles of sodium acetate are going to equal the moles of acetate ion in solution. This is a strong electrolyte, so however much we have equals the amount that dissociates our ion. And we know that we added 0.3 moles of this. We also know that we added 0.3 moles of acetic acid. This will be important in a moment. Here, this is our Henderson-Hasselbalch equation from yesterday. We know that our pH value is equal to 4.74, and we also know, because of that equation, that is equal to pKa plus the log of the base concentration over the acid. Now let me go back to our given information. Our base, the conjugate base here, is the acetate ion. That is the conjugate base of acetic acid. And like we said, we know we have 0.3 moles of that because this completely dissociates. Now we also know that we added 0.3 moles of acetic acid. In other words, our acid and conjugate base concentrations are equal. So this whole piece in red, this would be the log of 1 because these are equal, and the log of 1 is 0. So this whole piece in red we can ignore, which means our pH is equal to our pKa, which is the same thing as writing the negative log of Ka, is equal to 4.47. If we wanted to work this through the dissociation constant, we could calculate the dissociation constant from here, right? We can calculate Ka from this piece of the equation. We undo the log by taking 10 raised to that negative power would give us Ka. So let's make an ice table to get the rest of our information. So we've got acetic acid in our solution. We know that when we add sodium hydroxide, that's a base. The base is going to react with the acid in a neutralization reaction, just like we saw yesterday. So we've got this acid in solution. We add the base, which means hydroxide ion reacts with our acid in a neutralization reaction to make more acetate ion and water. So let's fill in our initial concentrations. Our given information told us that we had 0.3 moles of acetic acid. Our given information tells us that we had 0.02 moles of hydroxide ion. And because we knew our buffer solution contained sodium acetate, completely dissociated, we know that initially we also have 0.3 moles of the acetate ion. Alright. Again, because this is a neutralization reaction and this is a strong base, we can make this assumption that it will be completely reacted. That was at the end of yesterday's lesson. This assumption makes our table so much easier. We don't have to rely on an X. We don't have to solve for any unknowns here. We're just filling out the table. We assume that this one is completely reacted. So if 0.02 moles are reacted, stoichiometry from our balanced equation gives us the rest of these numbers. If we react 0.02 moles of hydroxide ion, we must also react 0.02 moles of acetic acid. If we react one of these and one of these, we produce one more acetate ion. So we produce an equal amount, 0.02 moles of the acetate ion, which means it's just a matter of addition and subtraction to get our equilibrium concentrations. Knowing those equilibrium concentrations, we can use the Henderson-Hasselbalch equation to solve for the new pH. We've got our pKa, we saw was going to equal the initial pH 4.74 a couple slides ago, plus the log we add in the new concentration of our base and of our acid, and we're able to calculate the new pH. Alternatively, without this equation, let me go back to our ice table, we would have needed to calculate, we would have needed to go through and calculate our hydroxide ion concentration, our hydrogen ion concentration, and then get the pH. This is a much easier problem-solving strategy. As a reminder, the couple of possible routes this can take: if we add a strong acid or a strong base to a buffer, we first need to determine how the neutralization reaction will affect the amount of the weak acid and its conjugate base. Then we use that Henderson-Hasselbalch equation to calculate the new pH. So these are the two routes we can take. If this is our buffer, we either add base to it and calculate the new pH, or we can add an acid and calculate the new pH. And in either way, we're doing these two steps: the new amounts of the weak acid and the conjugate base, and plugging those base and acid concentrations into this equation. Notice, thanks to the buffer, we see a very, very small change in pH with our acid and base additions. There are two more examples on the slides, and I've included the solutions, so go ahead and try and work through those on your own on the slides. Here's example 1. We've got given information, and we're calculating the pH of the buffer, the pH after the addition of an acid, the pH after the addition of a larger amount of acid, and the pH after the addition of a base. And so the slides will walk through those solutions as well, calculating the pH from the Henderson-Hasselbalch equation. Given our initial, we've got our dissociation constant, we've got our initial concentrations, and then using a balanced equation to figure out the final resulting amounts of each acid and conjugate base, and then using that same Henderson-Hasselbalch equation, plugging in the new values. That was A and B. Again, C and D follow very similar logics to part B. So do these in your notes for practice, and then come back to the solutions and see if you have any questions. We won't walk through all of them, so they go through pretty similar to that first example that we did together here. These are here for your extra practice. Alright, the other topic we discussed in the last lesson was titration. So we've got just a bit more information here, looking at titrations from a graphical perspective here in a moment. So to remind you, in a titration, a known concentration of a base or acid is slowly added to a solution of unknown concentration. And then a pH meter or an indicator is used to determine when the solution has reached the equivalence point, at which point the stoichiometric amounts of acid equals that of the base. So our indicator will change colors when we've reached that equivalency. So let's take a closer look at what happens here. When we start the titration, and as we go towards the equivalence point, the pH goes up slowly. In this example, we're titrating a strong acid with a strong base. So we've got a strong acid in our beaker, we're slowly adding a strong base. So we start here with a very low pH because we had a strong acid. And as we add base to it, our pH is slowly increasing. Now, just before and after the equivalence point, the pH increases rather rapidly. We had a slow rise here, a small slope, and then as we're adding milliliters of sodium hydroxide just before we're about to reach the equivalence point, we see this big, quick spike in pH, a rapid increase. And so that's what's happening down here. We went from our initial acid slowly reacting some and having some remaining. Here we approach the equivalence point where the amount of acid, the amount of hydrogen ions equals the amount of hydroxide. And then once we pass the equivalence point, for a brief moment, we also go through a rapid increase in pH as we go from equivalent to an excess amount of hydroxide ions at base. Now at this equivalence, remember, the whole point behind an equivalence point is that the moles of acid are equal to the moles of base. So the solution at this point is only water and the resulting salt from the cation of the base and the anion of the acid. We have no extra excess hydrogen ions or hydroxide ions floating around. If we go past the equivalence point and add more base, we will again continue increasing pH until we hit a fairly steady value, and it goes back to increasing slowly. So here we have two indicators that were in this solution. The methyl red color change happens just before the equivalence point here, and then if we overshoot it, that would be indicated by a phenolphthalein color change. So by bordering the equivalence point on either side of the pH, we can watch to make sure we don't overshoot it, or we would know if we had. If we titrate a weak acid with a strong base, we can look at that graph as well. So now we have a weak acid in our beaker, we're adding a strong base. Now, unlike in the previous case where we had a strong acid, the conjugate base of the acid is going to affect the pH as it forms. Remember when we had a strong acid, its conjugate base is negligible. But now that we have a weak acid, its conjugate base is basic, and it is going to affect the pH. As a result, the pH at the equivalence point is greater than 7, because at the equivalence point we also have some of the conjugate base, which is increasing the pH, making the solution more basic. For this reason, phenolphthalein would be the indicator of choice because it has a color change in this region. Again, the weaker the acid is, so if we look at the lines here for different acids going from strong to weak, with the weaker acids the initial pH starts higher because the acid itself is not as strong, and the change near the equivalence point becomes less drastic. So Here at the strong acids, we've got a very low starting pH. It increases slowly until we near the equivalence point, and then it really jumps. But as we get to weaker and weaker acids, this starts to get less sudden, less drastic. Here with the very weak acid, we've got actually a fairly rapid increase in pH here at the beginning, which then levels off as we head towards the equivalence point. Sort of from the other side, we could titrate a weak base with a strong acid, and this is just sort of the opposite thinking to the weak acid with a strong base. So this time the weak base is in our beaker, we're adding the strong acid to it, and the pH of the equivalence point in these titrations will be less than 7 because the weak base will have a conjugate acid that is influencing the pH, pulling the pH down to less than 7. And we could see why methyl red would be the indicator of choice here, as it's got a color change in that pH range. One interesting feature is we could also titrate polyprotic acids. Remember, polyprotic means multiple protons. And in these cases, there would be an equivalence point for each dissociation. So a point for each hydrogen breaking off and being at an equivalency point, which makes for a very interesting looking graph. And the equivalence point is going to be at these vertical sections here. Just like it was before, now there are just multiple. Alright, last topic for this unit is to consider solubility. So, here's another example equation. We're going to think about its equilibrium. When barium sulfate is dissolved in water, we get an equilibrium between the solid and the dissolved barium and sulfate ions. Alright, we already know that. We could write an equilibrium constant expression for that. That's not new, we've done that before. This is the, we've seen KSP before, we mentioned it briefly in our equilibrium section. This is called the solubility product or solubility product constant, KSP. And it's written just like other equilibrium constants, where we just care about the aqueous or the gas phases. Now, an important distinction, KSP is not the same as solubility. It's a solubility product constant. The solubility is the mass that is able to be dissolved. It's the possible mass we can dissolve in a certain amount of solvent. So for example, it would be expressed in grams per liter or grams per milliliter or in moles per liter, an amount that can be dissolved per liter. However, if we know the solubility of a compound, either in grams per liter or moles per liter, we can use that along with the solubility product constant to solve for the molar concentration of ions in our solution. We'll take a look at that. There are a couple of things that are going to affect this solubility. The first one being the common ion effect. Just like in the last lesson where we saw how having an ion already dissolved would reduce the dissociation of an acid, the same thing is true when we're dissolving a solid. If one of the ions in a solution equilibrium is already there, already present in the solution, then the equilibrium will shift to the left, towards the reactants. The solubility will decrease. If we were trying to dissolve barium sulfate in water, we'd get a certain ratio here based on the solubility product constant that would be in equilibrium. But if we were trying to dissolve it in a solution that already had sulfate, our equilibrium would shift towards the reactants. We would dissolve less of this overall because there was already some of this ion in solution. Another factor that we need to take into effect is the pH, because as we saw in previous lessons, different ions, especially metal ions, have an acid or base property to them. So if the substance has a basic anion, it's going to be more soluble in an acidic solution. If the substance has an acidic cation, it's going to be more soluble in a basic solution. So we need to think about the ions in our solid, in our substance, and consider their acid and base properties to determine what pHs they're going to be most soluble at. And finally, there's this idea of complex ions. A complex ion, recall when we talked about Lewis acids and bases. Metal ions can act as Lewis acids and form complex ions with Lewis bases in the solvent. These are a couple examples of complex ions. So it's a metal ion that is bonded to a Lewis base, and you can see its equilibrium, the equilibrium equations written out here. And those will experience different solubilities as well. For a fun fact, if you remember the iodine clock lab that we did, the reason we saw a color shift there was because we were forming complex ions. I'll talk about that in 1 second. The formation of complex ions typically increases the solubility of its salt. So we've got a solid here. It could dissolve to just make its ions, but if as it dissolves it's able to bond with other substances and form complex ions, it will become more soluble. So we can see here that not all of the silver chloride dissolved in water. Only a portion of it dissolved with the water. But when we add ammonia, we're able to dissolve it completely, and that's because the silver and the chloride ions the silver ions in particular, form complex ions with the ammonia, and so have a much better ability to dissolve. Another factor is amphoterism. Remember, an amphoteric metal oxide and hydroxides would be soluble in a strong acid or base because they can act as either. To be amphoteric meant it could act as an acid or it could act as a base depending on the conditions. Examples of these include aluminum, zinc, and tin. They can go either way. If you put them near a base, they'll act like an acid. If you put them near an acid, they'll act like a base. So these are soluble in either. So on your homework, some of your questions ask, they give you a set of conditions and ask if a precipitate will form. And so the way to calculate that is to use Q. So if you remember Q, our reaction quotient, just like we compared it to the equilibrium constant in our past unit, we can compare it to the equilibrium solubility product constant in really the same way. So if we have a solution, if Q is equal to our KSP, that means the system is at equilibrium. The solution is saturated. The solution has dissolved all of the compound that it's going to, and it's at equilibrium. If Q is going to be less than our solubility product constant, that means the solution is able to dissolve more solid until it reaches equilibrium. It's going to dissolve more solid. It's going to make more product, more dissolved aqueous ions until we get Q up to equaling K. Now, in the case where Q is greater than K, that means we have too many products, not enough reactant. Our product was our dissolved species, our reactant was the solid. If Q is greater than K, then the salt needs to precipitate. The solid needs to leave the solution until Q is back down to equaling K. So here's a flow chart. Goes through a couple rules because I think in your homework problems we only will ever have one step precipitation, but you can use selective precipitation, which would utilize the difference in solubilities of different salts to separate a mixture of ions. So we've got all of our common possible ions up here. This is just an example of what we could do to separate them out one by one. Let's say we had some concentrated hydrochloric acid. We could calculate what would precipitate there. We'd find that the group 1 insoluble chlorides would precipitate. And so any of our silver, lead, or mercury that was dissolved in the solution would precipitate at the addition of hydrochloric acid. And everything else would remain in solution. And next we could add H2S, and the second group, any of these ions would precipitate because these are insoluble sulfides. All of these bonded with S. See, here we added hydrochloric acid, we're adding chlorine ions, we're forcing things with chloride ions, salts that form chloride ions to precipitate. When we add H2S, we're adding sulfide ions, forcing salts with sulfide to precipitate so that we can go back to equilibrium. And we'll still have the rest left over. Next, we might add an H4 to S, thereby forcing out any sulfides and hydroxides that cannot remain dissolved, so all of these color-coded ones. And we have the rest remaining. We could add either of these acids, force out this last color-coded group, the insoluble phosphates. We added an acid with phosphate in it. We force out any of the salts that form with phosphate. And finally, we're left with these last couple. We'll add NH3, ammonia, to precipitate out these combinations of our last couple ions. So that's just a general one option, one thing we could do. If we had a whole group of these dissolved, we could separate them out selectively by group. Typically, let me go up one slide, we'll just be using this bit of information. If you're asked if a precipitate will form, you should look at calculating Q and comparing it to the solubility product constant. Alright, that is all. Hopefully that went well. Work on your homework. Let me know if you have any questions over this material. Thank you.